sovereignty. So that they want to be independent from like the US or those markets where today it's dominating the industry of computers and stuff. So it's a political decision that Europe wants to become more independent, wants to have digital sovereignty. And of course that will fund many different areas. Yep. So it will fund the area of digitalization so that we can move away from old ancient business processes, especially in the public sector. Yeah. It will fund investments in novel technologies like quantum computing that might come and be very, very interesting. But it will also fund traditional supercomputers. With traditional, I mean like the next generation of the supercomputers that also, I mean, we're doing supercomputers now in so many years, even since we started, doing back in the days, those real old computers, were also funded by the government of different reasons. I mean, we had the space race, we had the race, the Cold Wars, and before that we had the chasing of how to decipher the different, communications during the World War, Second World War, and those kind of things. So they were all funded by somebody because there was a reason to fund it. But and now the reason is digital sovereignty for when it comes to Europe.
But don't you see a risk of Europe investing in, for example, quantum computing, which actually is a hobby interest and a favorite topic of mine as well. Actually written a quantum computer program once. But anyway, don't you think that could displace investments that could go into proper AI otherwise?
Potentially, yes. But I think we have to do both. There's always going to be branches of technology. One branch is quantum computing, one branch is traditional supercomputing.
But the angle I think is interesting here is that yes, digital sovereignty. I can't even say it.
It's very hard. I know.
I haven't even had a beer.
It's one of those words we can probably never learn to say unless you're like native speaking.
No, but the goal and mission is clear and sound. Now, how to get there and what does it really mean and what tech should be on your forefront to get there in the best way for Europe. And here I think that's the interesting topic now. If you think about quantum computing, for me is not even Agenda 2030, it's almost like Agenda 2050. And we want sovereignty now. So what tech is more relevant from now to 2030? And then this is one angle. The other angle is, dude, the tech giants of the world, what are they doing? Why aren't we simply doing what they are doing? Why do we do something else? Do we think we're going to leapfrog them?
There are parts of the European decisions which lean in that direction as well, like, having a healthy IT industry also in Europe, having service providers also in Europe who will compete against the giants that exist today.
But only from a tech perspective, there's obviously some sort of proven tech out there because some people are worth billions and doing something right. And if I just sneak behind the scenes, what tech are they using? I would start there, as a non-expert. Because HPC and the supercomputers, then we solve problems in one way. I mean, like even in weather forecasting and now actually we're actually solving it in a different way, potentially.
Yeah, I think it's a big risk and I think, the argument that sometimes here politicians in EU claim to use is that, well, the big tech giants are investing so much in GPUs and TPUs and FPGAs and other type of AI hardware, so let's not go there. Let's do something else because they're already doing it, and let's find what else is out there. And then they say, quantum computing, no one is really doing that, no one is using that, so let's try something no one is using.
Oh, that's good, but it's a big bet, right?
It's super strange argument because, of course we want to have some kind of innovative, long-term investments in R&D, but you should also focus on what does actually Europe and Swedish companies need today. And that's not quantum computing, I can tell you.
But I mean, there is a number of initiatives that, during all of these years, I've been involved in some of these projects. And I remember when I was working for AMD, when I was responsible for some of the HPC activities we did in Europe specifically. Already then it was a lot of discussions going on whether you should, develop like novel computers or whether you should buy the standard off the shelf computing things. And And I remember that in the end of the day, you need to do some projects for the industry. So the industry needs to do some research, and it hasn't actually to do with about hardware, it has to do with software. So they need a specific software to achieve a specific goal, like developing a new engine or finding out a new way how to do fusion power and things like that. That was happening at that time.
Right.
So that when you have something that you need to do and you have a deadline, and you need to be ready by 2020 or something.
Then it becomes more crisp.
Then what happens is we need to buy a computer to run the software on, and then you buy one of these standard supercomputers which are available off the shelf. But always when you buy supercomputers, there's people who devote their life on hugging supercomputers. There are people who work every day with supercomputers, and they like to buy the latest and greatest. So in some of these initiatives already then, they are buying like what's coming next. So and sometimes that becomes super great, and they will buy like up and coming technology, which by then was there was some accelerated computers already back then, with GPUs back then. Remember the Blade Runner from IBM,
Yeah, the Blade.
Yeah, and some companies or some countries invested in that, and it was very brave. And it was potentially, they become very unique and they're world leading and so, but then the technology was didn't really survive commercially because of low volumes. So the thing about chip industry, and when you work with computers which are driven by computer chips, whether it be FPGA, GPUs, CPUs, whatever, is that you need volume. So you need the volume to have a sustainable business model for the company that develops and supports that kind of technology. And that was missing from that branch. That branch never had any volume. It was only available in the form of this and in the PlayStations.
Yeah.
And then the PlayStations opted for a different technology, and then you no longer had the volume.
Nothing.
Yeah. So then it's dead. So it will always be that companies or organizations or researchers that have a deadline, they need computing. And they will buy the best supercomputer or the best computer they have for the budget they have. And some people have a small budget. They will buy something great under the desk or consume it in the cloud. Some people have a big bucket of money, and they will buy the latest and greatest stuff, It's always been like that. I started working with this shit in the 80s,
It's
and in
always
the
been
80s,
like
it
that.
was the same in the 80s. Yeah. You bought, if you had $100,000 or kroner or whatever, you spent every dime. So you bought the coolest possible way you could computers that you could get for that amount of money that you had. Yeah. And I did it also at that point in time when I bought computers. And I remember the first time I was using computers in a commercial setting is that like this. So I went to school in Uppsala.
Perhaps we should just pause a bit.
Now we're moving into the introduction.
But that's an interesting story. But
let's go
we
here.
can get back to that story in Uppsala.
I think so too.
But
we have so many topics we touched upon already about HPC and different investments, and I think we should explore that a bit more shortly. But for people that don't know you, who is Leif Nordlund?
Yeah, Leif Nordlund, that's me. I come from a small town up in Norrland, or in Hälsingland actually, which is not so far away actually. So people sometimes think you come from Piteå or something, which is, I need to take a plane there to get home tonight. But no, it's only 3 hours.
North of Gävle is Norrland, right?
Yeah, exactly. You cross something called Dalälven, which is a large river,
exactly.
And then you're in Norrland. So I came from there, and my parents and family, we are like a traditional working background, So my father was basically a lorry driver or specialist in anything that has to do with driving things from point A to point B, and eventually specialized in some of that things that he was doing for his working life. And my mother was working as some kind of a secretary or a financial administrator in some of the small companies that we had up there. So with that background, you never thought you were really going to do anything else than potentially end up working in some industry or something. But I had other plans. So when I was really young, there was a show on television, Blixt Gordon, or Flash
Gordon.
This was the original
Flash.
black and white series,
black-
you know,
I remember
where
this.
you can see the strings hanging from, the rocket ships were sailing around on strings, and it was really I was really interested in that kind of things, robots, spaceships, and all that kinds of things. But
I had one of
then-
those small books when I read a Flash Gordon quite early, but Flash is even 50s, 60s or something like this.
Yeah,
the black and white.
black and white, and also remember that even in that series, Ming was already then played by the Swedish actor, the Max von Sydow. Already then, so he was kind of interested because he also then played Ming like 50 years later or something like that. So he must have been really young then. Anyway, so what happened is that I was interested in that kind of things, and I was thinking, can I work with something like this when I become older? Then it becomes really interesting. So what can I become then? Well, I can potentially become some kind of a soldier and pilot some kind of an advanced battleship or something, but then once you got a little bit older, okay, that's not going to happen yet. We don't have any advanced battleships or anything, and potentially I don't have any good enough reflexes and stuff to become a pilot anyway, and I probably have the same wrong body type to become. There was a lot of things hindering me from becoming a pilot anyway. So I decided, okay, what am I going to do now? So after graduating from college, I was thinking, what am I supposed to do? I have absolutely no clue. And then I have a friend who was starting 1 year before me, because I have to do the military service. So he was starting 1 year before me. He started in Uppsala on education there, was like in computers. And I was like thinking, okay, I wasn't really interested in computers, but it's potentially a good job.
It could potentially lead to Blixt Gordon.
Yeah, it's a much better job than going to some industry or something. It sounds really interesting to deal with computers. So let's go then and do that education. I will choose that education as well. So I chose this one, and when looking in the book then of available courses in educations in computing, I opted for the one called artificial intelligence. So nobody knew what that was back then. I mean, there was some guys. Maybe you, Anders, knew
What year
about
was this?
What year is it? That's the
This is the 1985.
Oh, okay. No, I don't think I got started that yet. So.
See, I was first then in this
I
room.
think
so yeah, so I thought, okay, this sounds really interesting, artificial intelligence, and I have read the books from people like Isaac Asimov, and those kind of things. So I knew a little bit about it from reading science fiction books. But I had no history with computers. I never programmed, did nothing. I didn't have a computer or anything. A lot of my friends had Sinclairs and those old early computers, but I wasn't interested. But I was kind of thinking it's a spaceship technology. Mm-hmm. So I went for it. And when I then went to school in Uppsala, I very quickly sort of, catched on the concept of this, that artificial intelligence is pretty cool. However, I'm not that good. I'm not that good. I think I started 86, but 85 I did military service and decided to apply for this. So I came to that school, and I mean, there was also a lot of other stuff going on. Drinking beer and and talking to ladies and things like that. So you weren't exactly devoting your life into computers, not at all.
A lot of strange distractions like women and beer.
And didn't you say you were actually responsible for the beer at?
Yeah. That was also kind of interesting. So we had every student union, which was basically a region of the country in Sweden. Then we had in Uppsala University, they had one house per region. So we had Västra Götaland for the western region, we had Norrland for the Norrlandic people, and then for the region I come from, which is Hälsingland, we had Gästrike Hälsinge, which is from my region. And it's a sort of, it's a small world. So basically when you're part of that, you know everyone and you become friends with everyone, and eventually I got voted as managing then for a period of time the running of the bar, basically. So that means purchasing beer and
sourcing and selling
beer. Not only beer, there was also other stuff, but I mean beer was the bread and butter. Of course there's also some caviar as well and stuff like that, but I mean the bread and butter was like the beer.
So let's put it this way: if you fail on the sourcing of the beer, that would have been would have been noticed.
Exactly. But it was also one of the first jobs I had where I had to be financially responsible. So you had like a budget, and you had to sort of produce some figures and so. So it was a good start also for becoming adult, because before that the jobs I had before that was like moving the lawn.
Yeah.
For in the summers to get some money to buy petrol and other stuff you need to survive in Norrland.
Yeah.
Petrol is really important in Norrland. You need to go somewhere, so you have to go a distance, You cannot walk. It doesn't work in Norrland. You have to go by a car or something. So
and that was a sidetrack. So back to the computer
but
story.
I mean, I like sidetracks because you of course you need to help me to get back to the original story. But anyway, I was handling the beer then, and we are drinking beer now. Maybe everybody doesn't see that right now, but we are drinking beer now. So this is some kind of a Swedish IPA, I think, that we're drinking. Cheers.
Skål.
So during that period of time in Uppsala, anyway, I did also start to work in a job which managed to guard some military facilities, or not military, but facilities in Sweden that was really important and couldn't be left unguarded. So that was my other job. So in the winter time and in the springtime, I was managing in the beer stuff and selling wine and stuff, and also bartending, mixing drinks and things like that. So important things to know when you are old, how to mix your own drink. So you cannot sit there and be reliant on somebody else to fix you have to do it yourself. That's called surviving strategy. How to survive. And my other job was guarding some military facilities in the summer. So I actually had my summer job. I had a gun.
Really?
So that also was kind of interesting. I don't think they do that anymore in Sweden, that they give it to part-time workers who get a gun and go out and guard a specific place. No. Well, then I did that. So, and we had a version then. We had the disease back then, if somebody remembers, it's also called AIDS. So it has nothing to do with AI, but it starts with the same letters. So I was also guarding some of the early AIDS patients because they were considered so super dangerous, So you locked them in and then we put a guard on them. So I was guarding them as well. But anyway, getting back to the story about Uppsala. So when I was in Uppsala, and eventually I managed to, of course there was a lot of hindrance during the way, all the beer and all the women and stuff like that. But eventually you graduated.
Yes.
And then I applied for some kind of an internship or sort of a thing in a company called Sandvik. And that's where my real history with computers really started. So because back then, they were very, very advanced in their thinking back then, Sandvik, if you compare to other international companies. So the whole strategy of Sandvik was to have a very lean and efficient supply chain managed by computers. So it all was all the orders all over the world from we were 144 countries where they were had an office or something.
And for people that don't know what Sandvik does, what do they do? Well,
it's a group. It's actually a group company with different industries involved in producing and selling things made out of steel, and everything from raw steel, steel things that you put into constructions, but also more advanced stuff, like cutting tools and stuff like that, which you put on really advanced industry things that produce advanced things like ball bearings and cars and things like that. So it's a kind of a broad company that makes things made out of steel. So
excellence in steel in all kinds.
Yeah, exactly. And sometimes it's not even steel; it's some kind of a powder you put in an oven, you bake, and out comes something called Coromant. So Sandvik Coromant is one of the famous parts of that group, Cool. But anyway, I was working there, and as my first job, I was kind of an intern, and those kind of interns, they normally they put them on some kind of an assignment, and my assignment was to. Goran, can you pick up the picture from Hong Kong? With the foreign-looking people there. So. Yeah, not that one, but you'll get there. Yeah, that was, you go back. So this is actually a picture I took myself. So So this displays then my first, like, job after coming out of the education in artificial intelligence.
Oh, really? And this is
So-
still in the 80s, right? Or the end of...
This is the 80s.
Yes.
It's still in the 80s.
So can we identify what PC is on there?
It must be
Yeah.
IBM, right?
It is an IBM machine.
No,
I think.
it's probably a clone, I would guess.
Or is it
They were
IBM?
building them already done in Hong Kong. Hong Kong was very big on clones. So my assignment there was to go there and put IT into the office. They had no IT.
Right.
So they were the last Sandvik, one of the last Sandvik offices all over the world that wasn't sort of, having IT locally. Because as I said, the whole strategy was to have all the offices with computers, and then every office was sending their orders, back to Sandviken, the city
Yes.
up next, as on the other side of Dalälven, up
Other
in
side.
Norrland now, up in
Yeah,
Norrland now.
what they call Norrland, but it's not really Norrland.
Yeah. So I remember I come there and they asked me, okay, go there and install this software that I got like on diskettes with me, or if it was tape maybe.
The big one, the big fat ones, the big.
Yeah. And okay, so I did it, and I had to go out on the street then. So the guy sitting there, if I remember correctly, he was one of those young guys. So the young guys really adopted technology quite fast. I had to learn them a little bit how to get started with the software package and so. But the older guys, they didn't really like it. They used to have a secretary writing all the orders and all the papers for them, and now they were supposed to do that work themselves, and they didn't really go. For them, that was a step down, in what you do during the day. We're going to now be out selling, or you're going to sit behind the desk. They didn't want to be behind the desk. So, but anyway. So this was the year that I think, if I remember correctly, this was the introduction of the 386.
Oh.
So
nice.
it was 286 computers that you see there is 286 computers, and if it was probably 386 computers for like the central server, and they were all connected. The computers were connected in the local area network.
It's impressive.
This was before the internet was generally available.
What is a 386 for the young viewers?
Yeah. So. Yeah, can we come back to that? Because
Yes.
If I start talking about that will take at least 15 minutes, and we get
So this is the evolution of the processor.
Yeah. Well, I get back to that. So
Good, I like it.
Yeah,
Let's do it like that.
yeah. But anyway, I went out on this. Went into a shop like you do nowadays when you buy shampoo, or if you want to buy some headache pills, you go into a shop for that specific sort of thing. This was a computer shop, so you went into computer shop and you bought some computers, and this was not traditionally the way things are done, But I mean, I didn't know, so I went out there and bought some computers, and then they sent an invoice of that, and then I installed the software package, and we had it up and running in a couple of days. And then I spent one summer in Hong Kong to sort of put computers then on the desk where they used to have typewriters before. So I've been part of that as well. This is big for me to be part of that, like industrial revolution. So taking away a typewriter and putting a computer on the same person's desk, that was a big thing for me.
But that's interesting, because we now have we can talk about your career and how you interpret the shaping of the compute era. Let's go this way.
Yeah, digitalization already back in the 80s. I mean,
Yeah, but
It's
really cool. Where now we have a story that starts with taking away the typewriter and putting the computer. Let's go. I like it.
Yeah. So I think we need to start to talk about, before computers, one has to understand the concept about digitalization, as you mentioned, Anders.
Yeah.
So back in the days, so many years ago, I think it was, let me see here, I have forgotten, which year was it? Somewhere around 1840 something, so very long time ago, 1840 something, if I remember correctly. There was two persons involved in digitalization, like inventing the concept of digitalization.
In the
1840s, yeah. So there was a lady called Ada Lovelace, and there was a guy called Charles Babbage, and there's been other guys involved. So you cannot like credit them for all the innovations. So, but the thing is that they had this notion that you could represent everything in the world with numbers. So that was the start of digitalization. So they sort of put that on paper that, okay, you can take everything in the world and you can represent it in number. Because these people were mathematicians. I'm not, by the way. So for me, this is like, a little bit over my head. But they had the concept that you can take anything in the world, a carrot, a donkey, or a animal, and you can make that animal into a number.
And describe it in mathematical terms.
Exactly.
Like this.
And if you can do that, you can also process it then, if you put it in numbers, because how to work with numbers and calculate things, that has been known for so many years before this. But this was the year or around that era that they found out, okay, if you can formulate your theory or problem or the thing you want to do, if you can take that and put it into numbers, then you can also call it digitalization then. And these numbers can be processed then in a calculus machine, or that Charles Babbage has some theories how to construct the actual machine. But I think it was Ada Lovelace that had this vision. She was the visionary. She was the super think, okay, we can do so many things with this technology. And he was like the engineer, Charles Babbage. He can actually do a blueprint of a machine. Oh, you put up the other picture that you had before there of Charles Babbage machine. There were the people. So this was before transistors and tubes and things like that. This was a mechanical computer. Yeah, here you can see the mechanical computer. So this is when, much later, they actually built the machine from a blueprint. Not while he was alive, though. So he sitting there working on his blueprints and thinking about these things. But I mean, this is very complicated. And who wants to finance this? It's always a problem with computing.
Digitizer.
Yeah, he was super smart, but he didn't have $1 million lying around so he can build this. But many years later, they collected some money and they built this computer that were to actually prove that it works, basically.
But I'm just curious. What was the term they coined? Was it digitization, or what was the term they used when they wrote their paper? Or do you remember? What were they calling it at the time? Now we have calling it digitalization, and we even argue what's the difference between digital. But I think this is the original coinage in some way. What were they calling it?
They said like this: the power of a computer rests on the concept that numbers can represent other things.
Yes.
So that was the whole thing. So that was the revolutionary thinking that they had. Like, numbers can represent other things than numbers.
I think an interesting anecdote here is that computer, actually before computers, was people.
Yes.
So people that sat down and actually did a lot of computation were people. And they added up stuff and did stuff you do in Excel today, but they did it manually. And suddenly you had computers, which was actually, a computer instead of humans.
There was actually
there was a term called computer, which was a human before computers.
And if you want to see a good movie on human computers, on television last week, they had a show on the hidden computers at NASA. It's a very famous story of how they had women.
Yeah, it's a series actually. So.
No, it's actually, maybe it's a series, but it's women, and then the whole game is also that this is in segregated America, and it was black women who actually went on and basically were some of the smartest in this. So the human computer is actually before the real computer.
Yeah. That is very true, and that was still the case during that period of time. But they thought they were so intelligent that they could sort of think, okay, we could with this technology we can do many things. But it never happened then because the funding wasn't available, technology wasn't available to really build these things. But a bit later, then they started actually to to get money. And why did they get money to build more computers? Who funded it? Well, it was basically the governments. So the governments funded the computers because they wanted shit to be done in a specific period of time, like urgent. They had some problem they needed to be fixed urgent. So some of the very first, you can show one of the pictures of the very ugly early supercomputer. Not that I'm going to talk about it, but it's a good picture showing that how a computer can look like. So not that one, it's the latest and greatest. That's one, yeah. This is one of the old supercomputers that existed, before they were made out of modern sort of chips and stuff like that.
And by the way,
cathode tubes and things like that.
But the computer is actually the wall in behind.
Yeah, that's correct. The other one is just
it's not the terminal. It's actually
maneuvering station. The other one, to control the computer. Yeah. So actually, this picture comes from the London Science Museum. So it's showcasing one of those early supercomputers. So why were they funded then? Well, it started with that you had the World War II. And then there's another movie about that. And what is the name of that movie?
The guy who is the code breaker?
Yeah.
I can't remember the name of the code
Imitation Game.
The imitation game with the code breaker computer, when he built the mechanical computer.
So there were two computers constructed basically around that time that is kind of famous. One was the Alan Turing machine that this movie is about. That was one of the first generally programmable computers that you were still programming by hand, so you were turning knobs and things like that to program, but you could reprogram it to do other things. So they actually made it possible that the power of a computer rests on the concept that numbers can represent other things that I mentioned before. They made it happen because they received funding, and funding is essentially if you want to do something.
Yeah.
So that was one of the computers constructed. The other one constructed at that time was for the nuclear arms race. So it was to develop basically a very powerful bomb so that you can kill the enemy. So one computer was to know what the enemy was doing, which was Alan Turing's machine, and the other one
was to calculate
the potentials of what you can do with nuclear technology. And then it's continued like that. You had the Cold War. After World War, you had the Cold War. So a lot of computers being built then to sort of simulate and develop new atomic weapons and things like that. That can really sort of be state of the art. And then eventually you had the space race to send rockets to places, and the space race ended up then developing a general term actually. Rocket science. So rocket science is the other term of HPC, high performance computing. So that is because back in those days, most supercomputers were made to calculate the trajectory of rockets and the computational fluid dynamics of a rocket flying through either the atmosphere or space, because it's different characteristics when you fly in these two places. And how to maneuver it, and having different kind of engines to power it and to simulate that. And so all these simulation technologies they were receiving a lot of funding to build novel, specialized supercomputers that was doing just that, received massive amount of fundings, and it was very, very expensive. What happens eventually, and we get back to the story about Hong Kong right now, and what happened then about in the mid-80s is that you had some guys who were a little bit dorky, as I was when I was also young. But they were dorky in a way that they really were interested in computers. They went sit at home and built computers, and also they had to have some kind of a software on the computers. And they had a vision that everybody should have a computer. Some people didn't share that vision, Ken Olsen and those things in the famous story. But these people, they made the computer personal, the personal computers. So when you had personal computers, you have something also at the same time, you have a very large market to sell that computer to. I mean, if everybody will buy a computer, you will of course have a lot of volume, and you need volume in order to have a sustainable business model if you want to do some kind of technology. So that sort of changed the whole story of computing, because now you can have cheap computers. Before, the computers were super expensive because you had no limit in the funds. I mean, you want to be first to the moon. You want to have the most powerful nuclear weapon. So there was no limit in the funding. But now everybody can buy a computer. So even I went out and bought computers in Hong Kong, to put that software into play in the Sandvik office.
But this story in the end goes always circle what tech to focus on to get sovereignty. I'm just waiting to die for that because it has implication on how to think. But continue the story. I just want to make that it all ties together. That the fundamental understanding why you went for supercomputer had one business mechanic behind it, and we're living in a different business mechanic with the personal computer entering the game.
Yeah, it does. And that what happens then is that, of course, there will be people connecting the dots. There will always be people connecting the dots, because not everybody has an endless amount of money to buy a supercomputer. So people they wanted a supercomputer, but they didn't have endless funding. They started building supercomputers based out of these, personal computers.
Networking.
So connecting several of these computers together, and to connect computers together, somebody already had invented that idea before. I mean, the beginning of computers communicating to other computers, that has a lot. We don't get into that today because that's also a complex history. But it ends up in the way that computers can be used also to communicate. In the way that they did Sandvik, sending in the orders to one place to have a lean supply chain, yes. But we can do so many other things. I can also send messages to people, mass sending of messages. So I can share my knowledge, or I can send my March orders to a large number of people, and I can direct an organization without having physical meetings. So it also is not only a tool for representing things in numbers. It's also a tool for communication and sharing and gathering of data. Gathering of data came later. First comes sharing, and sending out information came first. But then right after that comes, okay, now they're sending me back information. So now I'm getting a lot of information from a lot of people that I'm supposed to understand and collect. And of course you understand that, being a person like me, stupid and lazy, if they send me enough information, I can no longer process it. So I will need to have some kind of algorithm to process the incoming data. And that was the birth also of, I think, of the way to use computers to process data in different ways than just, orders and invoices and stuff like that. Is the fact that it is possible. It's an evolution. It was possible, so somebody will do it. And there was a lot of theories. I mean, when I was going in Uppsala in the university, artificial intelligence was software that you wrote which was rule-based. So it was written by me. I was the one writing an algorithm that was supposed to be intelligent. So it wasn't really AI as we know it today.
So the definition has evolved as well.
Yeah. So now the definition is more of a data-driven approach. You collect a lot of data because you get back a lot of data from people who are using your apparatus, your mobile phone or your computer or something, and they are all connected because there's a technology called internet that also came, And since that all happened, now we have an abundance of information, and we have powerful chip computers. So having an abundance of information at the same time as you have powerful computers, of course, then you can really do AI, and that happens. But it didn't happen until the 2000s. And if you look at the pictures I was showing you from Sandvik days, actually you can show the picture of the guy sitting talking on the phone there. Can be fun for somebody too. So when I came back from Hong Kong, this is how I looked back then. So. You didn't eat much when back in those days.
You're quite thin, yeah.
Yeah, very thin. And if you see, you had a very beautiful tie with one of those. It's actually not a clip. It's actually a branded saw, Sandvik saw.
Saw again.
Back then, Sandvik was still doing saws and tools. So I was writing software to manage that then. Yeah. So those were when I came back, I started working for that company and wrote software then to, process orders that were coming in from all over the world. But no artificial intelligence did. So this is the 80s. So no artificial intelligence. It was my brain creating the code. And that can never be great because I'm not that intelligent. So that can never be great. It can do stuff, yes. It can do stuff hopefully correctly, yes. But to do something new, groundbreaking and so, we need to move away from the capacity of a single person's brain. So we need to have a big number crunching machine who can take those things that can be represented in numbers, like data, collect enormous amount of data, process data with this very powerful technology, and then we will have something really intelligent coming out in the end. Not limited by a guy like that on the picture, not limited by a guy like his brain size or his visionary capacity and things like that. So now everybody is more, worried about that this artificial intelligence that will go out and do strange things, which we don't want it to do, but I'm not so worried about that. I'm more worried about things like you were mentioning, Anders, that for a country like Sweden or even Europe, to stay on top of this kind of new technology and not be left behind. It's important to be focused and really thinking, are we now doing the right thing, as you were discussing before?
Yeah, good question. And perhaps before we move into that type of topics, let's finish up your history a bit as well.
Yeah.
So you were in Sandviken a number of years, and if you just were to proceed a bit longer along your career, what happens next?
Yeah, so since I was then, I think I was little bit visionary at least, because I thought it was really interesting that you can actually do this large scale communication for a company of Sandvik's size, all the orders coming into one place, and also we also were very early on email at Sandvik, so we're doing emails, even if the emails were all in one computer, not sending them around, everybody was logging in to that computer and sending the emails to each other. It was still very good. So with that concepts in mind, I actually moved to Stockholm and started working for another company that basically, I wanted to come to Stockholm, and then there was this job, and I managed to end up in the insurance industry working for Skandia.
Right.
And with my sort of, ideas about how to do things, I quite quickly did a number of things at Skandia, was kind of interesting. So one was that we were one of the first companies to have a international email system, like to email then between the different offices, not in one computer, it's not like in a mainframe or something, but actually a decentralized email system.
And that was in Skandia, right?
Yeah, and I knew some guys, Mikael Runheim, if you know that guy, he used to have, he's kind of famous in Sweden. So he had a company called Elektropost. So basically that company was helping you to send the email from point A to point B. So from an email system in the office in Stockholm to an office in the US of the same company, then we could have send the emails back and forth. But this is before the internet.
This is before HTTP protocol.
This is before the internet was generally available. So this was all done on modem pools and modems and and then it was very expensive. I mean, back then you had to have good funding to pay the telephone bill. Everybody that used to be doing modems know that back then it was not so cheap to be calling into those BBSs. Back then it was something called BBS. For people that don't know, that is basically as a switchboard where a computer can dial in, and then you can connect to other computers and you can start sharing some interesting information. Normally the interesting information you shared back then was recipes how to make bombs, pictures of nude women and things like that, and also music. Remember, this was the first year that people had started bootlegging and sending music over these telephone lines as well, and downloading music. We were using the internet in the company to communicate between the different offices and to share ideas and make the company more efficient, basically. So this was very early, and right after that, a little bit later, this was the early 90s, very early when I came to Stockholm. This was about the same time that you had music, all the albums were black. You had AC/DC, you had Metallica, all the albums were black. So that was this period of time. So nowadays, there's more the T-shirts which are black nowadays. Yeah. But back then, it was the albums were black. So So during that time, it also became kind of when you were traveling, because we had offices in the US, so you got to travel to US kind of often, to help them or to synchronize the efforts that we're doing, writing software packages that can be used in different countries to manage the way that company was run. The internet was really booming, so the internet was really coming down, and that was a big revelation for me. Because now you can connect computers and you can use computers for interesting stuff, more than just to send orders. You can send big things. You can send movies over the internet. So you're not hindered anymore of the limitations of the modem technology and the slow telephone lines. So we were one of, when I was working there. So we asked them the management of the whole company, and like the big Scania, the insurance company, we asked them, okay, is it okay if we set up a web server and to start sort of having a web page with our products and stuff like that? Yeah, it's okay. You go ahead and do it. So we got some funding for it, and we bought one of those. Back then, this was Unix servers. Yes. So actually, when you were going on to the internet, you couldn't use those personal computers to have your web server on. It wasn't really mature for that back then. It was too slow for that. So you bought one of those really expensive Unix computers, and you got it up on the internet, and so Scandia.se was the domain name, and it's for people that are really old and was living during the early 90s. They know that this was one of the first companies Swedish companies that had a website. Otherwise, it was universities. Universities had, because they were already connected to other universities and doing things in the shape of Sunet and those things, which still exist today. But this was one of the first companies that set up a web page. Enterprise web. So talking about the products, eventually having logins for customers, so customers can log in and do business with the company on the internet. And then we got Skandia Banken eventually, which I wasn't involved in, by the way, but that also came. So it was a very interesting time. And then that led to my new movement in work life. So I thought this was so interesting with the internet and these kind of things. So I actively managed to nestle my way into a company called Sun Microsystems. And in this World Wide Web area, when everybody was going to go online on the web and do, everybody wanted to have Sun technology for that. Of some reasons, they very good marketing, but also working technology. You can actually buy stuff that actually worked when you installed it. So they were building a lot of the early websites for companies were built on Sun Microsystems.
So I remember this. I worked at Uppnet Merkantildata, and basically we were first to take Cisco routing to Sweden, and basically this was the networking part, and the other part was the building big firmware service setups and storage and all this, and then it was very, very clear. One of our niches was the new ISP, Internet Service Providers. So we sold the shit.
More advanced than modem pools in the cellar. Some people were actually getting rich or having modem pools in rooms like this. Do people see this room in the?
No, they don't.
We're sitting in a cellar in Stockholm, central Stockholm.
But Internet Service Providers is a little bit later. This is
I know, but it started with modem pools in cellars like this.
And I remember we bought half of Information Highway. Do you remember one of the biggest?
Yeah, and remember them all. I had all of those customers, customers for these companies.
And basically, they one part went into become internet guys, and the hardware, the infrastructure guys came into the company I work for. So we had now Compact Digital, Unix stuff, and then it was, but Sun, damn, that was cool stuff. That was. Super hot. That was Apple hot.
I have some favorite stories about Sun myself. It actually was one of the first systems I hacked into when I was doing a lot of hacking and cracking back in the day. So yeah.
But do we remember why Sun was cool? Because it was cool.
It was cool, I think, as well.
Yeah, but it was several factors, as I said. One was the fact that it worked and it could scale up, but also it had a very cool software layers on top of the machine as well, so you can actually develop a little bit faster. And you had things like like Java and web server technology and things like that, and some of that technology also was developed on some computers, so that when you had when you won the developers on your heart, so you need to win the developers that were developers, and if they developed on your software, on your platform, they were also going to deploy on your platform. That is important. So you had to go out, and they were very, very good at seeding systems into universities, and then the people in the university, they
classic strategy,
eventually graduated,
get the students on it,
and then they came out in work life, and they knew about Sun, Solaris, and so two things: it actually worked, and it was also having a very, very broad customer base of these people coming out of schools,
And it worked also because they controlled both the hardware and the software to a large extent, right?
So
like
Sun Solaris was popular for the developer community, and Java worked well on it.
We call that a full stack approach, Anders. We who work in this industry. Yes, they were very early with the full stack approach, and that is exactly how. Now I work, in a company called Nvidia. Exactly the same.
Yeah.
Exactly the same. Full stack approach is the way to go if you want to do
What's the
something.
jump between Sun and Nvidia? So there's a couple of steps, right?
Yeah, many steps in between. But
what is the pivotal steps?
Well, the pivotal steps was actually, I think it was that if you work for Sun, it is kind of likely that you end up in Nvidia eventually. Some of the same people went from Sun into Nvidia.
So how do you, that story I want to understand. How is that logic? There is a logic here.
Yes, it is, because Anders cracked the story. It was the full stack approach. So you have to develop if you want to do something revolutionary in computing, you need two things. You need some really good hardware designers, but even if you have that, you can fail because you don't have two things: volume and software. So, and those two things are very interrelated. If you have volume, you will get software. I mean, if you build it, they will come. So if you have volume, you will get software. But also, if the software is scaling and working really good on your chip, that is also becoming kind of powerful, so that people can do other stuff with, because everything can be represented in numbers, as we remember from the 1800s. So we can actually do science on these things. And if you can do science on these things, people will buy it, because people need to do science, because they need to be ready with the project until 2020, whatever year they decide they want to be ready. So there's a sense of urgency. So if there is a sense of urgency, if there is a budget and there is volume, so you can actually have some software as well that is actually working on your platform, then you will become successful. And that was exactly how Sun was successful, and exactly how Nvidia was successful. Nvidia started much, much later than Sun. But Nvidia was becoming successful because they went into a niche industry which had volume. So because when Nvidia started, it was a lot about, enabling advanced graphics. And you have many user areas of advanced graphics. The most famous one is gaming. So, and the gaming is like for everyone. So everyone can buy a computer and game. So everyone can buy this technology, and you will get a lot of volume. And on top of that, people then want to use it also for other stuff, because people need to do science. So if you have really good technology and you have people who want to do science, okay, you have these scientists and they don't have an enormous supercomputer, every one of them. Remember, because there's no endless funding. I mean, maybe in somewhere there's endless funding, but I never heard about it. Oh, sorry, I did.
I'm tempted to say something here, but I should.
Actually, Anders, there was something called Bo.com in the 1999, 2000s, like a Swedish company, and they managed to get a lot of capital. They had a lot of money. They were a startup. They want to get it online on the World Wide Web and to sell basically clothes and stuff back then. And they had almost limitless funding. They had enormous amount of money behind their back, like investing into that company. As in many other companies, internet startups. This was a .com era. For people that want to read more about it, Yeah, there's a lot of books about the .com era, and especially there's books about Boo.com as well. So I had an order from Boo.com. So actually they phoned me one day. And it was like, we just want to have this list of computers, and they sent like a list they want to have. Oh, that's
Pretty
that's
substantial.
200 million Swedish bucks, or 20 million or 15 million British pounds back then. So yes, I will send a quotation to you guys. So do you have any questions or anything that we do? We have a dialogue, or should I just send you like a quotation? Oh yeah, no, you can send a quotation. So nobody was asking, how fast can we get it? That was the only question. No question about rebates, pricing, whatever. They just want to have this list of computers for like 200 million Swedish, and they didn't ask for discount, and they wanted to have it as fast as possible. So I made the quotation, I got the order, but then the financial director I was working in Sun back then time, said, no, this company has no credit history. It has no proven thing that we can risk taking this order, so we won't do it. Okay, so I was sitting there feeling like the worst salesman ever in my period of being a salesman.
But your financial director probably didn't know the backing of the investors.
He had his tools that he was used to working with, and so what happened is that in another country, in Britain, Sun took the order in Britain instead, because they had a larger company with more volume, and they were willing to take the risk of this, But they just required them to pay upfront or pay at delivery, and that was no problem. They paid at delivery. So they did the order then, but I didn't see that order coming in anyway. So that was the only time I've been working during a period that weren't endless funding was available. But the rest of the time there was no endless funding. Yeah,
cool.
So anyway, so getting back to the story then, what happened is that when I was then working in the Sun Microsystems, and there was a period of time when the personal computer technology, x86, as people, we mentioned the 386 before, so there's like 286, there's 386, there's 486, eventually there's...
This is the Intel chipset processing.
Yeah, it was a standard. They
right?
invented a standard, because this was also run a little bit by the governments, because the governments were funding it. So they decided it should be a dual vendor strategy. So the x86 is a neutral term defining an instruction set that is publicly available.
For the chipset.
And then you can be a licensee. So you can be an x86 licensee. So you had two competing technology vendors back then, Intel and AMD, that was doing x86 chips then based on that standard. And of course, when you have a standard and many vendors, you will have better pricing because you will have competition, and you will also have larger volumes, because when something becomes kind of popular, like a standard, like more people will write software to this platform, and the volume will be larger because there's more software available, the more computers there is need for.
It's a spiral.
Yeah, it's a viral, yeah. So that's how it happened. And so Sun had another processor technology called Spark. Yes. So it was like Sun's technology that also was actually also licensed, so together with some other company, the way they were doing these technologies. It was not only Sun, but Sun was somewhat controlling that ecosystem, like Intel is controlling the x86 ecosystem. It was similar. But the volume was so much bigger on personal computers,
Yeah. I think the time is really flying away here, and we have so many topics that we want to cover.
Do we? Do we have topics to cover? I didn't know that. Sorry for that, Anders. But anyway, so just cutting that story short then.
Yeah.
Because the question was this: how did you end up at Nvidia from Sun?
Yeah.
So there was an interim step, and that was AMD. So AMD, I started working for AMD because the Spark chip wasn't really flying anymore. We weren't selling more and more. We were selling less and less. x86 was taking over because the volume technology. So for me, it was, I was then, at that time, I was responsible for Sun's x86 servers in Sweden. So for me then, to change from Sun, promoting x86 platform, into AMD that wanted to have a local person in the Nordics running the business, it was not a large step. It was a very, very small leap over like a fence, and then I started working in AMD. doing the same thing, promoting the x86 technology to companies and enterprises and supercomputing centers. They wanted to build computers based on x86 technology. And I remember traveling around in the Nordics, and in my first weeks at AMD, we were promoting a technology that was available on paper. So you couldn't buy it, but it was available on paper. So we were promoting then the x86 processor together with something called an accelerator. So like an advanced math processor that can do calculations much faster. We were traveling around with the different supercomputing centers and talking about this upcoming technology. And supercomputing is a conservative industry, actually. So they want to have the latest and greatest, yes, but they also want to have something that actually works because they need to get shit done. So they won't buy something that is novel. We mentioned quantum. So this was kind of novel back then to have an accelerator back then, because who was going to then write the software?
But at that time, AMD's biggest competitor was, I guess, Intel.
Yeah,
right?
Intel was the leader in this was the challenger.
Yeah.
Intel was the leader, AMD was the challenger. And the way that we worked in AMD to challenge Intel were two different strategies, I would say. One was to make systems that was better architected. So, and the other one was to invent new interesting things like this accelerator. Then, but accelerator never flew, so they never became a product of different reasons. Potentially not enough volume, and who was going to write the software?
Right.
So that was different from Sun, because at Sun we wrote the software. So Sun took responsibility for writing the full stack approach. So at AMD, we did not have the full stack approach. So we were working with the different ecosystem vendors, like companies back then, who was writing operating systems, people who were writing later virtualization layers, like companies like VMware and so, becoming more and more popular. So we had to work with those guys so that they had to write the software.
So you had the
We
full
delivered.
so you could actually deliver on this the whole story
Yeah.
to value for customers.
We were dependent on
Other
the
people.
ecosystem to sell this. So that was kind of interesting. And then we had the same story a little bit like Sun had, that Sun sold fewer and fewer Spark processor due to the fact that Intel was so popular with the x86 platform. At AMD, we had a little bit of a snag that the CPUs that we ended up with a certain year was not as powerful as the competition.
This is leapfrogging every year.
Yeah, they were a bit slow, and they were so slow that we actually sold so very little that we had to close down most of the offices.
For 1 year, we ended up in the wrong side of the leapfrog.
Yeah, I think it was a little bit more than 1 year, but because this was a big snag. It was a big snag. So potentially then, okay, the CPUs of that generation weren't super great, so they was not selling enough, so they had to lay off people and close down offices. So I was standing there for the first time in my entire work life without a gig. So I was actually unemployed for a while. I didn't know what to do. I had no clue, actually, because sometimes, like, now I'm going to do something completely different. You have that. Every person will have that during his lifetime. I'm sure that you guys have had that sort of thought somewhere. You're sitting there, now I'm going to go pursue my dreams and become a singer,
open a bar or something.
Yeah, open a bar, or
surfer.
play guitar, or become a professional singer, or and things like that. So
The 40-year crisis, right?
yeah. So I started actually working for a startup because I knew some guys. I didn't like that so much because I had been working with American companies for more than 10 years, and this was a startup. Startups are very different. I'm sure that you have worked with startups, all of you, I think. But I had no experience working in startups. For me, it was a little bit of a, revelation and so maybe not the ideal way to change your career path working for a startup when you had so many years in the past working for American companies with abundance of resources, and now you have very small resources. And then I left that job, and then I started working. Okay, let's go work for one of my previous customers. Let's go work for a supercomputing centers who use these supercomputers, and yes, I did that for a while, That was actually kind of very interesting learning thing to
You got
work.
another perspective.
Yeah, to work with supercomputers from the inside to make the users happy and try to make something, actually connecting it to scientists, working with the scientists who actually want to go and do something. And then after that, working with that, then I went back to the selling side because I got a selling job in one of the organizations in Sweden that was selling this kind of technology. And then I met Nvidia.
Before you go to Nvidia, because I think that's a topic in itself, and I think a lot of people would like to hear how that got started. But you worked with HPC and supercomputers before that a bit. Can you just mention some examples of what type of supercomputers are we speaking about here? The names of them, who was creating them?
Yeah, I'll tell you about it. So when I started working with supercomputers, which was then at Sun Microsystems actually, we were first selling the Spark supercomputers to customers, which was based on the Spark technology. So very, very, very powerful chips, very, very expensive chips with its own operating system, proprietary operating system. Still, it was Unix, yes, but it was Solaris. Then came Linux, really changing, because Linux were running on the x86 platform, and you can connect a lot of x86 computers together with the Linux software stack, and that became more popular. And then I was at AMD selling that kind of technology too, and I was traveling all over Europe then selling to research institutions this kind of supercomputers based on AMD technology. What happened after that is that this thing that I was mentioning, traveling around talking about accelerators, that shit actually happens. So people were actually started using accelerators, but they were not using the AMD accelerators, they were using Nvidia accelerators. So I was actually selling Nvidia accelerators then before I joined Nvidia.
Cool.
Because that was the latest and greatest.
And when you were working on the supercomputer on the customer side, what was the stack when you were on the customer side?
That was we had a combination of, we had x86 servers, like normal ones from brands like Supermicro and such, that's a good story, Anders. One of the computers that
You know what? We have to hurry up a bit here and catch up with the
destroying the whole concept.
No.
Too many stories to share.
It's so much.
I think that it's flowing quite well, so let's continue.
You asked the question, I have the answer.
We know, but this is the story of computation as a way to understand where AI is going, in my opinion. Because if you see the journey, there are several patterns here that tells us something also about the future.
Yeah.
But I think we should come to Nvidia.
Yeah, but we'll come there, and we are there now. So accelerators became popular at supercomputing centers because they were so much more powerful than CPUs.
And what is an accelerator concretely?
Basically, it's a massively parallel processor compared to a CPU, which is designed to do a number of tasks, but to do it, the number of tasks in a more of a serial way. So first you do this and then you do that. So since the technology was from the beginning developed for that, to do first one thing and then do the next thing, that is called a serial or sequential technology. You do one thing, then you do the other ones. There's been numerous trials how to make CPU to become more parallel. But since the original design is to do one thing first and then you do the other.
But how narrow was the first parallel? When you had this parallel technology, they were quite more for certain tasks, or were they really good at everything?
No, it was. There were many different companies trying to make parallel technologies. We can call them accelerators. So you can have accelerators made with FPGA technology. You can have them made with some other novel chip or whatever. But the problem is that you need to have two things, and I mentioned it before. You have to have the really good hardware designers and also a full stack approach. With full stack approach, I mean you have to control or develop the software yourself, and you have to have a lot of developers also working with you, an ecosystem, or so we call that volume. Volume is consisting of both the software and the hardware and the people. Those three things are the volume.
But just to be specific now, we are talking about the very low-end OSI stack software to run the hardware. Or what are you talking about? How far?
No, we are talking about
all the way.
tools that can help you to process data if you want to do AI. So
bottom line, so software meaning like I have great
full stack, so the whole stack, all over to what you want to do.
In the end, if I want to run something business-like that is going to use parallel computing, i.e. GPUs, it needs to be built so it works for this.
Exactly, and somebody has to fix that. And as I mentioned, and in some companies and some approaches are that they will work with other companies who will write the software.
Ecosystem.
And then you have and then you have companies like Sun and Nvidia which have a full stack approach. And the full stack approach is that you write most of the software, but you also have a large volume installed base with a lot of other users who wants to use the technology, and they will write complementary software. And that was happened with AI. So the early AI researchers that really made AI breakthroughs, they discovered basically that GPUs were ideal for the job. It was not discovered by Nvidia or people there. It was discovered by people that were wanted to do something, and they were having urgency to do that, and they did not have massive funding. So they had to go for cheap technology. So they found that the GPUs were the cheapest way to get massive amount of computing to complement your traditional x86 computer. Because x86 computers are cheap and generally available, yes, but they are not super powerful. So there's a limit of how many of those cheap x86 computers you can connect together in a big maze of networks. There's a limit how good the performance can become out of that, because you can never be massively parallel, because there's going to be too many complications when you connect 10,000 or 20,000 of those cheap nodes together. It's becoming too problematic to sync up the job.
Because the original idea for a graphical a GPU is graphics.
Yeah, and graphic is painting a picture on a screen, and you cannot wait for it. Has to be massively parallel, because you cannot wait for the dots to come up on the screen. It has to be for the eye, visually appealing. And that same technology can then be used to do massively parallel and basically hide the latency. Because as I mentioned, if you have a lot of computers or a lot of cores or whatever you have a lot of, you cannot have your algorithm to be sequential. Because if your algorithm is sequential, you will hit the problem of latency. So you have to have a parallel algorithm. Somebody has to write the software. It has to be parallel that can use those abundance of compute technology that is available in a GPU or in a room full of connected computers. If the software is massively parallel and you manage to hide the latency. So if you can have a method of working with your algorithm that hides the latency, then you have the full stack perfect approach. You have a good ground technology and you have a good algorithm. And that was the early AI scientists did just that. So the early AI scientists, they discovered a way to do that by having something called a matrix multiply. It's like a matrix. It's basically a thing you do over and over again in a massively parallel way. And the reason you want to do that is to analyze a piece of data, and you analyze that piece of data can be pictures or videos or collected data of some other kind, and you analyze that using these algorithms, and eventually when you have analyzed enough of it, you will have an answer, and the answer will be something called a model, and the model will contain a knowledge about a specific subject. In beginning it was pictures of cats that everybody knows. So they were competing with algorithms that can recognize cats on pictures, basically, on GPUs.
Perhaps we can also speak a bit about how you got started at Nvidia, and this was in 2016, 15, or 16?
Yeah.
And
so the reason was basically that I was already selling that technology because I was a salesman and I was selling supercomputers, and when I was selling supercomputers, I encountered, of course, this was the upcoming technology.
Yeah.
Because the reason it was upcoming, because it was gaining popularity because it's been around for a while. But at the same time, it was just recently popular with AI, and AI was booming. So it was had a long history. Yes, it was mature because people were using it for
Graphics.
and graphics and gaming and some other computational heavy stuff like simulations. But to use it on analyzing data was kind of fresh. And so that's how I started. Oh, you remember, Anders, I went to Uppsala and I studied artificial intelligence in the 80s.
Yes.
So, I can work with AI now. I can have a job, which is like have AI in the title. And that's why I went to school in Uppsala originally, to work with AI.
So the full circle.
Yeah. No, and I never got to ride this spaceship or whatever. But my life is not ended yet. So maybe there is like a solution for that eventually. But right now, I'm happy to work with AI and work for Nvidia, because I could finally go to sort of, where I originally thought I was going to get into when I started in the IT business.
So at that time, I think Nvidia has just, before at least 2015, it was mainly used for graphics, right, for gaming.
Yeah, up to 2012, I would say. In 2012, there was some early developments there where this was really becoming popular.
Was it popular at that time? I think AlexNet was one of the first one that actually started using GPUs.
But I'm talking about it was
time.
popular in starting to become popular in supercomputers.
Yeah, okay.
Because it was more mathematically more powerful than the CPU, so it was gaining popularity. Even if people had to write the software, yes, it was. But it was a good tool stack. It had a cool stack called CUDA. And the CUDA tool stack was easy for people to get started with. It actually could program a GPU in an easy way to reap the power of these mathematical operations that inside.
Yeah, so CUDA is something we can speak a bit more about. But I remember seeing the market cap for Nvidia, and if you look at that throughout the years and you see 2016, it's like an extreme increase. Like exponential increase, I think, in 2016. I think they tripled in market cap in 1 year or something. Now, people argue, is that because of the use, they switched from not only using for gaming and started using AI, or was it Bitcoin, or what was it?
It was a combination of all those things. Yeah, so it was not a single event. It was a combination of all of those events. I also remember that it was when people actually had availability of the data that is required to do AI. Yeah. So it was not only that the technology was available, also the data was available. Yeah. So at that time, people were starting gathering data because, it can be interesting. Because before that, people was basically putting your data into files and folders in your cellar of your office and not looking at it again. And they had a rule like you have to save it for 10 years for financial reasons, but no other reason to save data. So now for the first time, I actually had a reason to start saving your data, because you can do things with your data. You can mine your data.
And at that time, we didn't have any problem with GDPR and this type of legal issues that we may have today, right?
Yeah.
We could easily store the data. Cool. So you started working at Nvidia at that time. And for people that don't know really what Nvidia does, I mean, of course, I think they know the GPUs, but it's so much more than GPUs that they actually do. What would you say the main products that Nvidia has are?
Well, the main product is still the GPU, so that's the baseline technology. But what people do at Nvidia is to research, invent, and work on ways to explore and use that powerful technology in order to get things done. So that is the whole purpose. So we have more people employed at Nvidia working with software than we have people designing and working with hardware. Yeah.
So
we are trying to. I mean, we started having this, CUDA and some other things that can make it possible to use the GPUs.
What is CUDA?
CUDA is basically a abstraction layer that to talk about, in the way that you should talk about these things from a technology point of view. But it's a language how to program your GPUs. It's a language, but it's really an abstraction layer of the underlying technology, because you have to have a parallel computing technology, and CUDA is massively parallel in its nature. So that wasn't available.
It's a coding language done for parallel computing.
Yeah. And specifically for underlying technology which has a lot of cores.
But let me be the idiot here. Let's talk. Let's break down the stack a little bit.
Yep.
So we have the GPU, and in the GPU we have the chipset. Could we now dress up Nvidia that we said the difference is full stack, and here we only talk about GPU. Now let's could you please educate me on the I don't know what all these things are happening.
Yeah. So first you have the hardware, which is in nature then designed to do graphical stuff, which is massively parallel, and as they said already in the 1800s, if we can represent it in figures, we can do things with it.
So this is the hardware, right?
Yeah, so that's the hardware, but also the concept that if you have enough hardware, you can do interesting things. That comes back from Ada Lovelace and Charles
And what is
Babbage.
the next fundamental part of
to
this
make
stack?
to make this interesting for people to actually use it, you need to be able to translate then the knowledge you have in your brain into mathematical algorithms, which can then be programmed onto a chip technology.
Yeah.
And that abstraction layer, to make it possible to take your ideas or your representation of things into figures, making those figures understandable for a computer, you need something called a compiler or actually a language translator that can translate your language with
This
your
is the machine compiler.
Yeah. With you need some technology then to translate your code, your representation of ones and zeros, which doesn't start at one and zeros. It starts with some kind of a language, and that is called a programming language. So programming language is the thing that you put in as a user on the screen with your keyboard, and you write, I want the computer to do this. Okay, then you have to take that software and compile it in a way that it runs on a specific technology. And of course, the language has to be able to translate then your ideas, your algorithms into something that is efficiently run on the underlying technology. Yeah, and that's why it's important, like for Sun and like for Nvidia and those kind of companies, it's important then to have a tool which is make it possible then for a lot of people to take their intelligent ideas and make that run efficiently on a computer which is powerful. So that was the underlying sort of business
And what is this
reason
called?
to buy a computer.
So, and what are the layers? CUDA is the language?
Yeah, CUDA is the language. It's actually started out as a university project, so it doesn't actually come from Nvidia from the beginning. So, and when Nvidia started working with those people, we thought this was a really cool technology, because before that you programmed in a much stranger way, more of a graphical, telling the GPU how to basically paint a picture on the screen, which is a different one story, So now we don't want to paint a picture on a screen. Now we want to do some kind of an intelligent mathematical operations with the original visions of Ada Lovelace and Charles Babbage. So these people who wrote that language, they later then joined Nvidia and started working for Nvidia, and developed then CUDA, released in that name a little bit later from Nvidia. So when CUDA was released, then we went out to a lot of brightest minds in the different universities and research institutions all over the world, and started to help them to get started on CUDA. And it grew in popularity, but it took a long time. So this is not something that happened, like you said, like exponentially overnight. So this took like 10 years before it became more. So it became kind of popular in 2012, I would say. 2012, they more and more people were using this and finding it good enough to actually get a lot of things done. And then at that time also the AI scientists found this technology, and when they were using it, they were winning the competitions over the competing technologies. So there were other ideas how to do AI, which were running on CPUs, but this was so much faster. And AI is parallel in nature. AI, you don't have in AI to do first one thing and then the other thing. In AI, you can chop up a problem into small pieces and do a massive parallel computations, because it's all mathematics. So it's parallel mathematics. And that leans itself very good to GPU technology. It was a perfect marriage. So very good technology from Nvidia in the form of parallel computing architecture. On science area, if we can call AI a science area, I don't know, but I mean a way to approach doing things with ones and zeros, which will represent the things from the real world. Then, like the original vision from Babbage and Ada Lovelace. And at the same time, the availability of the data that is required to do this. Because, I mean, if you look at before the 2010, there wasn't any large data sets really stored in a way that you can actually access them in a quick way. And because now storage was also becoming, cheaper to buy by the gigabyte or per the petabyte. So they can actually have a storage system also containing a lot of data and easily accessible by these powerful computers.
Let me continue. I'm sorry, but I'm playing like I think this is quite for many. So let's say I'm a data scientist and I'm working in the CPU world. And I have come so far, so I'm at Python, right? I do stuff in Python or Julia, and I'm really intrigued now. I want to try out to get whatever I'm doing down on GPUs. So what's the path now to be a Python CPU programmer? What do I need to do in order to get my stuff into the GPU world? How does that, what is happening here?
I think that's... in that specific case that you are describing, it's a no-brainer.
Do I switch? I mean, Python, and then I use switch.
The Python is already an abstraction layer where you don't need to know that you have a GPU underneath you. There are some other...
so you can, from the Python, tell that this will be a parallel process?
Python has a complete one-to-one connections to GPUs.
Yes.
Because Python is a new language.
Yes.
So it was already developed in the mind of being parallel. So, but if you look at some older, like the Pandas and scikit-learn from, actually driven out of France, some of these technologies. So those technologies they were written for CPUs. And Hadoop and those kind of, when you connect a lot of x86 computers together to process large data set, that has been available for a while from Databricks and Hadoop.
The big data Hadoop stack.
That kind of stack. That was written for x86 computers, not for GPUs, not for massive parallel technology. So those languages that exist in that world is Pandas, scikit-learn, and those kind of packages. Those are just recently been ported to GPUs. So it's more of a journey there, because then you need to change your directive. So instead of using the directive that tells the algorithms to do it on a CPU, you want just to change the directive to do the same thing but using a GPU. So there you're either working on a library level or on an object level that you do a little bit of a change of your code, and then you can start working with GPUs on a massive parallel architecture.
So in the bigger frameworks, this is sort of fixed.
Yeah.
Or how do you see it?
Well, Panda or Python actually is rather... I mean, it's not super old, but in the beginning it wasn't supporting GPUs, but it's certainly easier today thanks to TensorFlow and PyTorch and all these kind of languages that use CUDA underneath.
So they're actually, what they are doing is they're working, you're working here, but behind the scenes they build the stuff that compiles it into CUDA, that compiles it all the way down to GPU.
Yes.
So so you didn't need to shift to CUDA programmer.
No, unfortunately not. It's kind of fun to write CUDA kernels and whatnot, I think.
Well, Robert Luciani says that was one of the guests, one of our good friends here, is like, dude, I just wish people were building stuff more hardcore, but he's like...
but like Julia, for example, that is much closer and has like GPU and differentiation at like first class level in the language. So some languages are a bit better.
So Julia is actually quite much closer to parallel.
But Python is by far the leading, of course, when it comes to AI and to use Nvidia for that type. So it's like far ahead.
Yeah, in terms of the size of the community.
Popularity, volume, as you say.
Volume, as you highlighted, yes.
And that's a very smart way to work, also from speaking like an old guy that used to be lazy. And I'm still lazy, by the way, so that's not unique. So when I was a programmer, because I was that when I was young, maybe that wasn't really I was programming also back then, in the Sandvik and Scandia days. Abstraction layers are kind of important, because if you don't have abstraction layers like CUDA or something like that, you need to do a lot of work. You need to sit in there and write a lot of code to do things. And people, even though it's really, really funny to write a really fast and optimized code and something like that, the problem is that in 2 years' time there will be a new CPU technology or GPU technology, whatever underlying technology, and you need to go and do your work again. So if with abstraction layers, I don't have to do the work again, because there will be a layer in between translating my good ideas into the underlying massively powerful computing technology that's underneath. So as Anders described before, it is so that languages which are recently invented or recently modified to support GPUs from the ground up, then it's a no-brainer, as I said, to work on that technology. But languages or things that are older, like the language C or Fortran, for example, there you still have some work to be done in order to fully support massively parallel architecture, basically. Because you don't want to support just a GPU. You want to have a way to work in a parallel way so that you can write parallel algorithms. And don't care about what's underneath, because people like Nvidia people or other people will do that kind of layer for you, the CUDA layer or whatever layer it is. They will do that work for you. And we happen to, that Nvidia owns also the Portland group that makes this kind of technology, the based out of, what city do you think it's based on? Yeah, good one, yeah. So they make that work for you. So instead, you just make sure that whatever you're using have a good abstraction layer down to the powerful platform. So you don't need to go back and do your work again.
I think that's one of the core reasons for the success of Nvidia, who is by far, of course, the leading AI hardware and software that we use today. And it's really you can't switch away from CUDA. It's so powerful that it's, even if you have AMD and others that you work with as well, Leif, it's really hard for them to catch up, because they don't have the software and the full stack approach, right?
But they have very powerful hardware, so it is always good with some competition. And being an ex-AMD as well, I have rather good insights into pros and cons of the different company cultures and the way they think about things. And so speaking from like a ex-employee of AMD and Sand and a current employer of Nvidia, the important thing is that there will be new technologies, there will be new ideas how to do things and so, but it's important with these abstraction layers so that people can adopt these new technologies. But somebody has to do the abstraction layers, and with a full stack approach, Nvidia will do this for you. So that is the powerful force having the full stack approach means that you have a very good chip technology and you have a very good volume of what you're doing. So then the volume will make it also then available for many people, both in the form of software and in the form of users and in the form of being in everybody's computer, available in everybody's computer.
To developers as well. If you make the software good enough so developers can easily use it, that will have a huge effect on the scale, right?
Yeah.
I think that's really one of the ways that Nvidia have succeeded so well.
Yeah, but the competition and the fact that we'll have multiple suppliers of technology, that is also a political decision, as I mentioned. So there's a political decision from the beginning in the US to have multiple vendors of x86. Then you have a political decision now that Europe should have its own digital agenda and digital sovereignty, so that Europe should have its own technologies as well. And we had technology in Europe, ARM, that was coming out of the UK. And then that was sold to the Japanese, and then recently Nvidia won a bid of actually buying ARM, because Nvidia has a vision that it's actually important to also have a CPU, not only a GPU. That was like the whole story of Nvidia, is that you need a CPU and a GPU. We don't have some kind of vision that you don't need one or the other. You need both. So that's why Nvidia wanted to buy also ARM, and we'll see how that will turn out then.
But I think we should pause on that because I think it's an important topic and a rather controversial one that some people...
It's not controversial.
I think so, and let me explain why. And Nvidia already has a rather big lead when it comes to data processing in AI and, of course, gaming and graphics. And then buying ARM, they also get a big hold into the mobile hardware or software. Would you not say so?
Well, back before I joined Nvidia, we did have technology and stuff for mobile, but it was too early. There was no need to have, and there was no battery technology as well to support very advanced graphics and GPU capabilities in mobiles back then. So they sort of left that venture, and so did most of the graphical vendors back then. So, but of course, if you don't care about now, I'm not talking about Nvidia or where I'm working, or more about my thinking about this area. Remember when as I said, when the internet became very popular. So there's been no technology before that was adopted so fast by households than the internet. So not the refrigerator, not the washing machine, not any other, not the cars, not the internet was the first technology that was really adopted by the whole households in a really rapid, in a 10-year period. All households basically had some kind of an access to internet in the Western world. So, and that was then accelerated by the fact that you can be having access to the internet 24/7 in your phone. But it started with the personal computer, and then it became the phone took over and became the tool to access the internet.
Yeah.
And to have the internet always on. And that was, if you remember the old slogan from Sun, anytime, any device, and there was a lot of videos which you can look on YouTube, how Sun was describing the future. They got some things wrong in that video, early 90s, but they got the hairstyles wrong. So they thought the hairstyles in the future were going to be the same as in the early 90s, which is not the case. You had these large hairs, round like microphone cuts on everybody. But the other thing they got wrong as well was that in that vision, when they was assimilating information into the computers, they were using scanners. Because they weren't thinking about the effect of digitalization. They thought that information was still going to be largely available in printed material. So if you look at those kind of videos, you put the material onto the screen, and then the screen assimilates the information, and then it becomes digitalized. So that was the vision back then. Now, when we are later in development, things are more and more getting digitalized from the beginning, so that we can work with digital data all the way, end to end, sort of, And that leans back then to the question about this thing with the mobile phone and the technologies like ARM or Intel or so as a underlying. I don't think that is the important thing really about.
Why do you think Nvidia bought ARM?
We haven't bought them yet.
But
so Nvidia hasn't bought,
but they paid like 40 billion or something for it.
They have made a bid, and now we're negotiating and stuff like that. So I cannot comment on that because I'm not involved at all in that. But
sure.
But as an Nvidia sort of following Nvidia before I joined, and now working at Nvidia, of course it's a subject which is really interesting, and I personally hope it's going to go well. So we'll see what happens. But as I was going to lean on the fact that you think it is so important, Anders, that you said it was controversial, and I don't think it is controversial, because I think the power of the future is the data, not a specific chip or something like that. It is the data and where the data is stored, and we should be more worried about who is collecting all the data about me as a person and my sort of interests and. I'm more worried about those things than worrying about what company has a specific chip technology. Maybe all those chips technology anyway will be replaced by some other new superior technology like quantum computing, overtaking everything. The important thing is that our code, our data processing has to have abstraction layers so that we can move in to whatever technology becomes, generally available, that is more powerful than the technology before. But the people that will have the power in the future is the people that will have the data to make the software really that you can move between these different architectures. Those are the companies we should be worried about. We shouldn't be worried about like Nvidia if we have a CPU technology or not that we can license. Otherwise, we can license and build an ARM technology with an ARM license. That is still possible. But it was like somebody had to buy ARM because it was out for selling, basically. And then Nvidia was one of the companies putting a bid for it, and it was a winning bid. So, but it's not finalized yet. So, we'll see what happens.
You have a good point there. The data is really core, but it's also a core to have great computational power available. And I've personally been playing around with the GDX A100 and seeing the power that these type of latest Nvidia machines have, which is really impressive. And perhaps we can move into that topic a bit and go a bit into HPC in general, because that's a field of expertise of yours.
Yeah, I've been working with that too long now, so I'm trying to get away, but it's not really possible when you're as old as I am. So you keep getting back to your sort of, your technologies.
That's happening a lot now. When we mentioned Europe when we started this pod as well, and we spoke a bit about the investments Europe is going to do, European Union. I mean. And we're already seeing these big HPC clusters in Finland, and we have Nvidia Superpod in Linköping University now called the Berzelius, etc. But I'd like to just give a background, remind you of different types of HPC, and it would be fun to see if you agree with that or not. So I think there are a number of different types of HPC. One is the more traditional one, which is the supercomputers, the crate computers,
the rocket science,
the rocket scientists,
rocket scientists, I guess, and they had a different type of hardware, different type of software, and different type of applications. Applications like weather forecasting or biological simulations and things like that.
Written by humans. The algorithms are written by an intelligent guy.
It's not data-driven in that way.
Exactly. So it's an intelligent guy who wrote the software.
Yeah. Not an intelligent machine. Cool. And so that one layer. And you mentioned as well, I think, the big data part of it, or tier of it. So big data is different. It is not...
It has a different history.
Yeah. And it's different machines, different hardware. It's kind of mid-range hardwares, x86 CPUs.
CPU-based ultimately.
But still, it's usually parallel. I mean, it can be hundreds of thousands of
But it's parallel in a
machines.
different way. Hadoop is it's a different ecosystem.
Yeah, so that's different software then.
And it's dependent on the network to become parallel. Yes. So it really requires a lot of,
high network
good network capacity. Well, it still was the case with the supercomputers as well. But I'm just saying that since it is an art of working with data, of course it requires a lot of I/O.
Yeah. Okay, so we have the supercomputers and we have the Cray machines and the applications they have. We have the big data tier, which has different hardware, different software like Hadoop, Spark, etc., and different applications, which is all the tech giants are doing, being data-driven these days and building data pipelines and need to process a lot of data and the KPIs and the business intelligence you need to do that. And then you can think of a third potentially, which I guess we can call it AI, and that's a different set of hardware again. It's GPU-based, like NVIDIA machines. And it's different software. It's the PyTorch and TensorFlow and CUDAs of the world. And once again, it's different applications. So this is more like building data-driven solutions, using data to actually build up the rules instead of manually programming, as you mentioned a number of times. And then we can find completely different type of applications compared to the traditional HPC or supercomputers and big data. And potentially we can have the fourth one, the quantum computing, since we have already gone there. Bit about that. And once again, you will see different type of hardware. We need quantum computers suddenly, and certainly different type of softwares. And I would say certainly different type of applications once again. Would you so far agree? At least we can identify a number of different tiers of HPC. Or would you call all of these HPC type of tiers, if you call it that?
But you are correct that you have a history of different branches developing evolutionary into more and more better solutions in that specific stack.
But we see these 4 branches. It's branching now they're all evolutionary. They're all getting better and better.
Yeah.
But we can see 4 distinct stories.
Mm-hmm.
Do you agree?
I agree. And we shouldn't forget the fact that this was early recognized by the Nvidia that I work for, that we identified that, okay, there will be a sort of, the different branches will come together, because that's the way that the new data center in the future will be built.
But will they?
Yeah, they will. So you will have to support all of these branches, in the data center of some kind. Maybe not quantum then, but the ones with the history, the ones that have that more than 10 years of history,
I think big
they will
data
come together.
Why won't we have a Betamax? Why don't we have a Betamax moment here? Why will not have a Betamax moment? So we are betting on Betamax versus VHS, supercomputer versus big data versus like this. And I'm now going to bet, as you said, unlimited funding on Betamax. You know what I'm saying, right? And are we betting on Betamax in Europe? Or how should we hedge our bets?
No, I think that my personal thoughts on this is very much that, since Nvidia and also myself recognize that eventually these technologies will fuse. And maybe not quantum, because quantum is still a novel technology, but the mature technology with a history. So you have all the Hadoop stack with how to store and process data. You have the classical rocket science HPC, which is about simulations. Exactly. So it's actually simulations.
So we have different uses.
The simulations is working with synthetic algorithms written by a person, which does so that's simulations. And then you have AI, which is software which is written by software. So it is a different.
Let's be explicit now. The hypothesis is that they will converge. And what is driving the conversion is that they are suitable for different use case applications. Is that the simple? Why will they merge? Why do we think that?
Because you will buy computers because you have a need to do compute. And you are a researcher, even if you are a researcher with 20 years of backgrounds of being like really good programmer. In the example, you had one example, weather forecasting. Let's take weather forecasting as an example. We can also take drug discovery as another example, how you'd find a new treatment for a specific disease.
Which is, by the way, is changing now, how you think about that.
Yeah, so both these were made with simulations before. So you simulated how the weather was going to be based on mathematical model, and the same for drug discovery. So they had mathematical models of how molecules work with other molecules, and you tried to find like a new drug based on what you knew about this. And it was written by humans, the code. Well, the difference now is that when you have a data-driven approach and you collect a lot of data about a specific virus, or a specific weather phenomenon, because based on the history of
we are out
competing
the supercomputer now.
And then you get a different way of doing the same thing. So you get an AI algorithm which is really good in doing the same thing that the human brain was doing before with his code, but it's proven numerous times to be both more precise in the prediction of what is going to be the good drug or what the next day's weather is going to be. So it's better on prediction, but it's also running faster on modern hardware, because it's not software that's written by a human, so it's written by computers, and they also can, from the beginning ground up then, in an architecture that can really make use of things like GPUs, a massive parallel computer. They can make use of it in a way that maybe the handwritten code wasn't able to do before. So with those facts, we know that the combination, even if you're a scientist that when are really, really good in molecular biology or whatever your domain is, you will recognize the fact that the AI algorithms are faster and more precise. And if they are faster and more precise, you get two effects. More precise, you can do your job better. So that is important for most scientists or researchers or people in the industry. They can do your job better. That is interesting. If they are faster, what does that mean then? Well, I can do the same work cheaper. And we can agree that in most cases there is not abundance, limitless funding. So it's not limitless funding, meaning that I cannot, even if I was a really good programmer before, I needed a supercomputer that costed like 150 million US or something to do my work. And that is not realistic for one scientist's work, you know. So instead, you will have, if you have these AI algorithms, which are, in a different way written and more parallel in nature and require less number of nodes, because the nodes which are parallel in nature have things like GPUs and stuff inside. You need a fewer number of nodes to do the same kind of work, and which is faster because it's just done in a different way. It's done parallel by software written by computers, which in that case becomes much cheaper than available to do the same work as you did before with handwritten code on these large experiments or proving a thesis on a large supercomputer. You can do the same thing with an AI algorithm. You will still need that others.
Why?
You need to correct.
Okay.
You need to check that your work is not going, because it's still because in science there is something called that you need to prove your theory.
So by having two different compute approaches, it's also a way to validate.
Yes, everybody that knows the history of science, or the definition of science really, is that you have a theory and then you have to prove your theory.
The hypothesis.
And at least for numerous years ahead, we need still to prove our theories. I think in one way we need to prove them in the old way as a reference material. But we can do then when we know that our algorithm is sort of working and it's actually precise, then we can at day-to-day use, we can use the AI algorithms, because they are requiring much less expensive hardware and much faster to get the result out of the computer. So you can get the result out in a couple of days instead of waiting weeks for the result to run on the classical
supercomputer. But shouldn't then the AI investments of Europe, or the hardware HPC investment of Europe, follow that fundamental logical principle of validating against each other? That sounds like a really good idea.
Well, but they do in certain. Well, Anders mentioned that they are spending a lot of money on quantum technology. That is true, but they're also spending a lot of money on the Euro HPC program. And in the Euro HPC program, they are funding a number of supercomputers which are built just with the best available technology. So it's basically a process where they are buying a number of supercomputers now in Europe. I think the total number is around 10. 3 of those are pre-exascale computers. So exascale is like, a vision of a really powerful computer that will soon be available, but it's a little bit out what you can build with today's technology. But with pre-exascale, you can get really powerful computers for a reasonable amount of money, because it's based on volume products like GPUs and CPUs and hard disks and things that which are produced in large quantities. And 3 of those supercomputers are going to be in Europe now. For the first time, Europe will actually be very high, at least for a while. I mean, I remember maybe before I was born, Europe was really big on supercomputing and really leading in the world. I don't remember that, but as long as I've lived, and I've seen the dominance of the US and also competing then with China has been the competitor. Well. Yeah. That has been the competition really. But for now, for the first time, with this investment that Europe is doing in these 3 supercomputers, we will have 3 supercomputers really high up on the ranking of the top 500 or even the top 10 supercomputers then. And these are bought with, money investing then in what is available today.
But are they balanced?
So we're not spending all the money on quantum.
Yeah, and let's hope they continue that way. I'm not as confident as you are that will happen, but I hope they will continue in that way. We just have like 10 minutes left, and I think one thing you said, and just to give some number to like weather forecasting, as you said, is something we do at Baltarian, for example. We traditionally, if you do it in the old style, it's basically simulating the physical world, as you said. And I think it takes like 3 hours for SMHI to do like a weather forecasting, a single one, and it's using a supercomputer worth like millions of euros to do that. And you can basically train an AI model today that costs 100,000 or 10,000 euros or something, and it can do a single forecast in a fraction of a second instead of 3 hours. I mean, it's insane how big the difference is, and it also is performing better. So I mean, I think that's that's a really interesting use case. And the same with drug discovery, as you said.
Exactly.
And instead of simulating, you have this AlphaFold 2 that do protein folding, and I think it went from like around 50% accuracy to above 87 or something. It's a huge improvement.
Yeah, what is
by switching.
AlphaFold? For you used a small topic, because I think this is one of the biggest news that came out in the last 6 months.
Yeah, so it's a DeepMind neural network that basically can do protein folding. So given these kind of proteins that you have, the sequences, it can actually predict what the 3D structure should be. And that problem of converting from the sequence into a 3D structure is called protein folding. And usually
so it's actually going back. So remember the old Ada Lovelace and Charles Babbage. You can represent anything in numbers. So one thing you can represent in numbers is DNA. So you can take DNA from the human body or from a dog or from a plant, and you can do what is called DNA sequencing. You will turn it into digitalized format of that specific thing. And one thing that you can digitalize then is proteins. Yeah. And proteins, if you have the digital representation of a protein, which you've done all the work, now you have the digital. In some cases, you want to see how it looks, like how the visual representation is. So you want to go back into the real world. So you want to take that numerical thing and
have a look at it.
Basically print it. And that is AlphaFold. So AlphaFold is predicting how it's going to look based on the numerical representation of the object, to go back then and look, okay, this is how it's going to look if you want to look
as a molecule.
Exactly. So that is really interesting technology. So you go from, first you have something, and then you digitalize it, and then you can print it. And I think you're going to print a lot of things in the future.
And what is the core neural network style? CNN, scans, transformers?
Yeah, more CNN based so far. Not transformer yet, but it's probably coming soon. Cool. So, given, I'd like to just bring up some topics, and you can choose, Leif, what you want to focus a bit on. I think one topic would be interesting is BioBirch, that I know you know a lot about as well.
Yeah.
And that could be one topic. It could be another one more about like different type of vaccines and how they're developed.
But these things are all related. So
right?
Yeah, they are. So basically, if you want to do something in the industry of pharma or in research in about the human body and things like proteins, and the reason you do it is probably because you want to find out more about the human body, more about the proteins, but also how the proteins are possibly then not perfect, and maybe you are carrying some disease. The disease can either be in the form of a virus entering the human body. It can also be what is called a genetic disease. You have something wrong in your DNA that you got from your father or mother that's going to lead to a specific disease later in time. So there's a number of reasons you want to know about the human body and how it works. Both the DNA, but also how this kind of disease can potentially be treated then. So if we can treat genetical disease like you're born with, that would be magical, So there's a lot of work going on in that area. But the more famous recent work has been around, we got this big pandemic thing going on in the world, really? COVID-19. Yes. So a lot of the work has been recently about how to construct then drugs in a faster way to treat a specific disease. Yeah. So a lot of these supercomputers that we have sitting here and saying that they've only been used to calculate, nuclear, atomic bombs and things like that, they've actually been used now to in the serving. So actually the whole of 2020, most of the supercomputers have been devoted to working on these kind of problems. And that has meant that we know a lot more stuff now in 2021 than we did in 2019, because of the focused work that's been done by all the scientists and all the supercomputing centers on COVID and how to do different vaccines and so. And some companies who had already collected a lot of data, I think Moderna is one of them that had a vision that you become more of a digitalized company already some years back. So some companies then have been able to produce vaccines in a record short time, because normally developing a drug takes more than 10 years, and most of those, like 90% of those experiments using old methods, they fail. But if you can do more work faster in a supercomputer, you have a better chance of succeeding. And I think we have now a number of vaccines against COVID that is out in the market, and we also at the same time also have a number of new things we can do with supercomputers that relates to this. One is, you mentioned AlphaFold, to look at how a protein is constructed. Another thing we can do is Google deep variant and variant calling on DNA to look at how to learn more about, variants in DNA and stuff like that. So there's a lot of stuff going on in this industry using supercomputers for life sciences. So not rocket science anymore.
But
now
life
there are
science.
life science computers,
That's a new hot term.
life-saving computers,
So
life-saving
life
computers.
science computing is the new hot term.
Yeah, it used to be rocket science.
You're a life scientist.
Now we always
Yes.
like to have a T-shirts.
A life scientist.
Data scientist crossed over, rocket scientist crossed over, life scientist. Life
Yeah,
scientist.
yeah. And
We should do
so
that.
That's AI. That's AI.
And that's what I work with currently. So I work in the life sciences sort of area now inside Nvidia, and it's been really fun during the it's been fun during the pandemic from that. So it's been fun during, like, it was really interesting work going on all over the world. But it has not been fun being stuck by a computer every day, not being able to travel and meet people. But I mean, it's
from
been
a science point of view, it's
From
been
a science
interesting.
point of view, from the pandemic, we've talked about this before, it has shown us also in some ways what we can do, how fast we can move, how fantastic things we can do, as long as what you said before, you need to have urgency. Like the problem is when we don't have real urgency, we don't take the right decisions.
But remember, we have had urgencies before. We had World War II with the Alan Turing machine and the code breaking and stuff like that. We had the Cold War and the space race during the 60s, 70s, etc.
So there's been drivers.
And now we have a new driver.
accelerated.
The pandemic is the new driver, So the pandemic's really accelerating.
It actually follows the history of what's the urgency and the drivers, where we then make a leap, even in the computing.
Definitely.
History.
I think that's a great segue to perhaps one of the final questions. I think you have very concisely and nicely described the history of computation in different ways, even back from 1840s and forward. But if you were to have a forward-looking view on this, what do you think lies ahead of us in coming 10 years when it comes to computation? Or longer?
I think two things. One is that AI will become more widely spread as a way to process data on computers, because still the handwritten codes are still, quite popular. Yeah. But AI will become more, because it's much more efficient to use AI to process data with computers.
But I don't think people understand that we are talking about the new coding paradigm. I think very few people understand it like
I know.
this.
It's just a new way of coding computers, to simplify it. But it's computers writing the software instead of humans. So that is going to be very big.
But that simple statement changed the whole mindset and outlook on what you're doing. This is not advanced analytics or BI. Forget about that. It's new way to write code.
Yeah, but you need data in order to write this code. So that means that when you say predict, I predict the data wars. So I predict closed borders, firewalls, and you don't want to share the data because the data is the new gold.
Data sales is the new gold because it's producing
So that
code.
is what I'm not worried about who owns what CPU technology or GPU technology. Who owns the data? The data wars is what I see in the future.
So Star Wars, Cloud Wars, Data Wars.
And I also see that since you remember the history that in the beginning that the computers were not connected, and then came the internet, and then became the supercomputers when they are connected. So network technology will be important in the future.
What do you mean with network technology? Are we talking the
technology
ecosystem?
is how to process data from point A to point B, because we need to read that data, share that data, send the data at least within our organization. Maybe we don't want to share the data. We
but-
want to send it inside our organization in a
You open up
controlled
a
manner.
Pandora's box, because I've been thinking a lot about the architecture of a distributed architecture.
Or decentralized, I think. Is
Yeah,
a better
Yeah,
term.
exactly.
Maybe
And
what's
that
the
is what I
difference?
think the
What's the
technology is
difference?
heading.
Yes.
This is good. What's the difference between distributed and decentralized? I liked it. I like this comment.
Yeah, I can speak in length about this. But,
Shit,
but,
I need that one.
We have no time limit suddenly, because now we're going to talk about decentralized versus distributed.
Yeah.
Could we please take 5 minutes on the difference of distributed and decentralized?
But guys, we can continue. I think that the hot stuff are coming now. We finally came to today.
Yeah,
Yes,
you know
every
what?
2
If,
hours.
if,
Yes,
you,
okay.
if you don't mind, when we cut this up, we took a long time on the introduction.
There's no cutting on this. I can tell you that.
No, so the first part is almost, so maybe now this is, could we do it? I wouldn't mind.
Yeah, I can start and you can fill in perhaps. But my view, you have distributed training, for example, of models, which is basically taking, you have the data centralized to begin with, and then you distribute it out to a number of machines and to do parallelized training.
Yeah.
It makes it faster, but you still have the data first centralized, which is hard to do sometimes and not always possible. If you do decentralized training instead, you don't actually centralize the data first. You keep it decentralized.
Yes.
And that can mean data in the mobile phones and it never leaves the mobile phone. Or it can mean data that has, exists in a hospital and it never leaves the hospital because it can be patient journal text or something that's really sensitive. So, but you still want to train some model on it. So instead of extracting the data, you move the model to the data. And then you do decentralized training. And this is like federated learning and these type of techniques where you can train the model on a part of the data and then instead distribute the model instead of distributing the data. So that becomes more decentralized type of structure.
And I see it also, if you want to talk about what is technology which could be coming potentially, I'm not sure, but I'm having like a crystal ball then. You mentioned quantum computing.
Yeah.
I think that what people are missing is that the computers that we saw before on the picture, the really old ones, they were made of copper wires and transistors, and before that cathode tubes. But transistors and copper wires between the transistors are the way that the modern computers are built still. So they're still based on transistors and copper technology.
So why don't we talk about nanocomputing?
So I think that what people are missing is that we have an opportunity to make it much faster by moving away from transistors and copper into pure light-based, photonic-based computers. And people are missing that because people are now thinking about quantum computers. If we think about the computers, how they work today, if we translate that from transistors and copper wires into a full optical layer, you have solved two problems. You have solved the way to how to make them faster. When we can't make them faster in silicon, we can make them faster using a different technology, fiber optics. Yeah, speed of light. So Nvidia acquired Optigot, which was a Gothenburg Chalmers startup who does fiber technology where you send the data from point A to point B, and that technology is very important in the future.
I used to work with storage.
Chips.
I used to work with storage, and we built SON network for the banks, right? This is back really early, right? So this is already here. We talk fiber. But it hasn't come further into the actual chipset. Not
for the actual chipset. So I envision a future where computers will potentially be based on photonic computers and to be photonic all the way, Maybe not in a couple of years, but in the end, because we cannot make the transistors smaller, we cannot do negative size. They're now at 5 nanometers. Yeah. We cannot do negative size.
It's a few atoms or something.
Yeah. So instead, if we want to make them even faster, now we need to move the quantum is one answer, but I think for a general purpose computing, maybe photonics is an easy way to go.
And what is quantum? Sorry to open up Pandora's box.
I am a strong believer in what you are saying, because I think that what we are confined with right now is the technology, how we have constructed all this computer is a copper and etc. In '86 there was like a research on a ore called lorandite. The whole idea was actually to create a supercomputer that is going to based on this ore capability to it's the only ore in the world that can actually attract the neutrino from the sun. right? So if you find like a small that invention that actually you can capture that in a small cube, you have solved the way how you can actually store a massive amount of data in a small cubicle. And that is basically the future. So I completely agree with you about that, because it's about new ways of thinking how we store data. It's not the other way around. If we think copper again,
store data,
done.
read data, and process data all in the same technology. We don't need to move. So we don't need to go from photonics, like fiber transmitted
exactly.
data,
And then
or back to copper and then into silicon. If we can do photonic all the way, I think we're going to get much faster computers. That's a theory I have anyway. And I wanted to, for the sake of the listeners, because I'm sure there are going to be a lot of listeners to this pod, I want to give a couple of tips for the listeners.
Good.
So, first of all, I already mentioned the movie, The Imitation Game.
Yeah.
So if anybody hasn't seen the movie Imitation Game, just go and see it, because it sort of shows why computers are interesting, when you have a specific thing you want to do, when you're really motivated, you can actually then not only can you create a specific computer architecture, you can also program it to do a specific task, and you can succeed in doing something that's not been done before. So that is the power of computers and working in this industry. If you have a good idea, it is possible to translate your good idea into something
but this is profound. We are missing 9 times out of 10 why we fail with data and AI operationalized AI is because the concrete problem is not concrete enough, and it's not translated into the mathematical or the representation in ones and zeros. I want to have better customer loyalty. This is good, but you need to start thinking, how would you translate that question into ones and zeros, which is the foundation of this conversation from the start, right?
Yeah,
and I think this is where a lot of the normal traditional companies fail. They haven't done this, business to data to in ones and zeros translation in their head. They haven't sharp enough defined the problem.
Yeah, and also I only mentioned if you look at that movie, The Imitation Game, that is one specific computer and one specific guy that the story is about. If you want to know more about the other stuff I was blathering about, there is a book. I have a friend who lives in the US, so he's called Merle Giles. So he is older than I am, so he is much better of the history of supercomputers than I am. So he has actually written a book then. So in his book, the introduction and history of supercomputing, I recommend that people buy this book and read it, because he made a lot of effort because he's been working in the supercomputing industry for so many years, and he sort of recognized the fact, okay, there is no good book that describes this history, and soon people who work with this will be dead. Because the rocket science, this is an old stuff. People will soon be dead. So he tried, before people are dead, he went out and interviewed and wrote a lot of
Fantastic.
Of documentation of what is known today then, before it is sort of lost. He wrote it in a book. So of course, this book is also digitalized. But you can get the paper version as well. You can order a paper version. So Introduction and a Brief History of Supercomputing by Merle Giles. I really recommend that book. I have a signed copy myself, since I'm a friend of Miles. So also, there will be a movie or some kind of thing coming out in the next couple of days. So watch out. So there will be a story on this computer that we are currently together with our partners building in Linköping, which will have the name Berzelius. That is one of these super powerful AI computers that has been acquired and to support the Swedish researchers and the Swedish research society and to keep Sweden competitive in all of this, AI area. So I really recommend you keep an eye open for that launch when that computer will be commonly available, and to these organizations that are involved in working with that supercomputer. So
And when did it go live?
it is going live quite soon. So
Quite
you
going live quite soon.
you will notice when it
So
goes
this is
live.
part of the launch.
Yeah, the launch is coming up in the very short period of time. So keep your eyes open now.
And what was the reason for the name? You know?
Oh, the Berzelius. So Berzelius is actually, so there are two guys in Sweden which are really, 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 really famous. And now you have to guess which ones.
Linné.
No, he nailed it. I'm impressed of this guy. He nailed it. So Linné is the most famous Swedish scientist, and number 2 is Berzelius.
Yeah.
So if you go, you know this Berzelius Park in Stockholm.
Yes.
There's a statue of him. So yeah, you can read all about Berzelius online, and he was very, very early on doing things to represent things with the numbers. But this was not in the form of digitalization in that aspect. But he was working a lot with
Categorization, classification.
Yeah, he was working a lot with but he was specializing in chemistry, I think. So he was putting figures on different substances, you know, to classify them. And Linné was classifying the plants and the
plants and the arts.
Yeah, the arts, yeah. So they were both sort of, you know, in that industry, in that area of
in the industry of classification.
Exactly. And both are internationally acclaimed super scientists of that time without using supercomputers.
Plus, Bernelius has LIU in it, which stands for Linköping University as well. So I think they thought
that was very, very smart.
And he also was born there. So he has
so
his
they
roots
have
there
many
as well,
reasons.
yeah.
Someone has thought
There's so many reasons.
This is actually a really good, cool name. I think
Yeah,
it
yeah.
has many. It's the game of classification. It's the, you know, you can choose whichever logic you want. They're all great.
But he's ranked number 2 of like Sweden scientists in history. So he's ranked number 2. So that's high up, you know. So number 1 was Linné, number 2 was Berzelius. This is, by the way, this is old from the internet. I had no clue on this before I read it on the internet.
So pretty impressive, you know.
So I did study this because I usually, since I work in this supercomputing industry, all supercomputers has a name.
Yeah.
And every time they get a name, sometimes I know who it is, like Linné. If a supercomputer is called Linné, I will know who it is. If a supercomputer is called Ekman, for example, as one of the Swedish ones are, I had no clue who Ekman was before. I had to I had to Google him and to find out who Ekman was, by the way. So it is, and another supercomputer that we had was called Tegener. So in that case, I knew who it was, so that was fine, you know. But still, I didn't know. Oh, can you name a supercomputer after a? I had to go and check it out.
What was the logic?
It was a famous scientist eventually, and I thought it was a poet.
And we've spoken a lot of Berzelius. Perhaps we should just mention some technical details. Do you have the details of how big it is and things like that?
Yeah, for sure. Yeah. It's
Can you name
well-known
something?
facts.
Yeah.
So at Nvidia, when we started doing this kind in 2016, when I joined Nvidia, we started doing. We call it then purpose-built appliances for AI. So basically, not a computer anymore. It is the full stack approach, as I mentioned like 28 times now during this broadcast. So it is a box with an operating system and a software stack specifically written for AI. So we sold them by the box in the beginning. So we sold two companies. Then, like, you know, I was selling it to the automotive industry in Sweden in the beginning. They were very early in adopting this, and then later on I started working with life sciences, and have life sciences customers now using it for things like drug discovery and such. And as part of this, we are now starting to sell this more and more in a way that you can build a supercomputer just for doing AI. So with that, it's a difference, because before we were selling one box by a time. Now we are trying to sort of think about, okay, how do we make this work in a larger scale?
Several boxes as one cluster.
Because that's normally how supercomputers are built. So this is supercomputers for AI. And they are called superpods. I don't know who I mean, pod, yeah. It's not this kind of pod that we're doing now, by the way. It's a different kind
I would
of
like
pod.
to understand
This is also a superpod, by the way.
This is a superpod.
This is also a superpod,
But,
yes.
to deconstruct the pod, if it's a cluster, how it's done.
It is definitely a cluster. So it's a cluster of a lot of GPUs and CPUs interconnected by a very fast network fabric. And by the way, we acquired Mellanox in order to make this technology really future-proof. We wanted
So your
to.
plane, it's a
We
it's a
also
fabric
want
plane.
to develop the network technology that will be ready for the future. So we as an integrated solution, we have now the CPU do some work, the GPU some work, and then the network processors do some work. But all together, it's called a superpod. So all this working as an orchestra playing symphonic music. We have some cellists and some drum players, and we have some flute players, and some people are playing the
Orchestrating.
violins and stuff like that. So all the people in the orchestra is there in the room, and in the former Besalis we have 60 of these DDX appliances, AI supercomputers connected to each other.
So is this one pod or several pods?
This is one pod.
160.
So in short, you could say GDX machine is one machine, right?
Yeah.
So 60
that
machines in one pod.
That single machine has 8 GPUs in it, and it's
Yeah.
the latest type of A100.
It is the
right?
latest one, but at the same time it also has one dedicated network port for each GPU. So that if you have 8 GPUs, you also have 8 dedicated network ports of
Times 60.
Mellanox technology,
Times
Nvidia
60.
networking is called now, and that
Oh my God.
and that all interconnected then in a massive mesh network, a switched network, so that you can now work with this as one big supercomputer for AI. So that is what it is.
So in short, it's 480 of the latest Nvidia GPUs called A100.
Yeah, but it's
connected
interesting.
together.
The 480 of GPUs, 480 network,
Yeah.
blah blah blah, and do you need to run a different type of operating system when it becomes when it becomes a pod? Is it specific software for pod versus running one machine?
No, it's these are all built in from the beginning in these DDX AI appliances. It wasn't of course it wasn't in 2016
But the software actually
introduced,
scaled from one appliance
but
to 60.
today we have written software. I mean, we started on adopting this technology ourselves in our companies in Nvidia. So we built a couple of supercomputers based on DDX technology before, and then eventually we started also to sell this into customer accounts where the customers were also using the same technology Nvidia were using internally to process and do their sort of AI processing on this kind of computers. And then we found out that actually this is a good concept, it actually works, and now we can actually go out and more broadly than tell the world about
General
the concept.
availabilities.
And we had to have a name.
Commercialized.
And we had to have a name. And then came the superpod. I actually don't know who invented it. Probably it was somebody in the US.
I think we should
in the
rename it
management.
AI After Work Superpod. That would be much more fun, actually.
Yeah.
That would be much more for the initiated.
Yeah, but it's kind of interesting that it's where this is sort of not only do we have the technology,
You can
we
sponsor
also
us,
have
by the way, and you can have the AIW Superpod.
Yeah.
And this time you need to have a proper GDX machine that works.
No, if you sponsor us, we can change the name
So
to
you know,
AI.
the funny story was
Let's do this.
when we opened the club, right? And when we
Yeah.
opened the place and etc.
Yeah,
So
tell
the-
us this story.
So we launched this place and it was
This is the
around
Hyperite
like,
Data Club. Sorry, guys.
Yeah, this was
What is the
2000
place?
It's a Hyperite Data Club. So it was
So this is where where we're shooting.
where we're shooting the pod right now.
Yeah,
So
it's
we
a cellar in central Stockholm. you know.
exactly. It used to be a huge bar for rental, but right now it's it's Hyper Data Club. It doesn't matter. It's still a club. It's still a bar.
No, it's Hyperite Data Club is still a bar.
Yeah, in general, yeah. So we opened like early 2008, I think it was in May, and the first event that we have, it was the launch of DGX2, right?
Yeah, that's correct.
So,
because there was a big event going on in Stockholm, like an AI conference.
Yes.
And
And at the
Nvidia.
same time, we had one of those very early boxes shipped, and Anders mentioned it was a dummy box. So
Yeah.
since it was traveling all the time, we didn't dare to use it for any to actually run it, because to dismount this one in order to be able to ship it, we had to take out some pieces and put it in special boxes, and there was a lot of dismantling, mounting it together.
But the
and all, so-
context is the machine is like a 200 kilo piece.
Yeah, it was a very big
we
one.
had to have like a
You need
big
to understand
wooden
this. This
box
is-
in order to put it, because
On
the
with
floors
wheels
were
on
not
it.
taking it. It was the floor was sinking.
So basically, you had the launch of the Nvidia. Which machine was it?
It was DGX2, but that was not the point. The point was that when we were at that point of time, we were thinking like this wine cellar that we have right now. It was supposed to be a super what is called like a place where we have different
Data
computers,
center.
data center, and then we have all the programs into data analytics and etc.
to showroom, yeah.
Yeah, where basically practitioners
still do
can
it.
come and then product test without any. There is like a
I think this is still a great idea.
It was, but it requires quite a lot of cash, man. It's a lot of.
no, he needs to. Leif needs to sponsor it.
so yeah.
Leif is a poor guy, by the way. I spend a lot of money on other strange interests that I have. So yeah,
Well,
one of
about-
those I just bought a summer house with my little cash. So I'm already behind on my
It's a good segue to the last two questions. So.
Yeah, and some that do have infinite funding is perhaps Nvidia, by the way. But okay, that's another story.
It's never infinite funding. There's that thing doesn't exist.
I like the idea that we need to talk to Nvidia for the AIAW Superpod.
Leif, what's next in your life? Personally, professionally? What's happening next?
Well, I am 55-ish, and of course I will work as long as I find it, great fun and can work for interesting companies like Nvidia. But I did buy a summer house now, which I intend to, in coming years, to build a better house on that property by a lake up in Norrland, in Hälsingland, and when I finally retire, I will concentrate then still I'm raising my daughters now as well, but I will continue raising my daughters and explore more of my favorite hobbies, which happens to be fishing and skiing and photographing and playing around a little bit with computers, but less and less actually.
And brewing beers, perhaps?
Yeah, but I'm not a nerd, so I'm not sitting there and documenting
You
in
need
a
to be
digitalized.
nerdy to really do really good
Yeah,
beers.
but I have a
You
lot
need to
of friends who are into that, so that I
can do it.
sometimes join them and sit there and try.
But you
out
can be
different
the taster, right?
Yeah, but I'm still. For me, beer is really, really good, but I'm also interested in eating good food and talking about interesting subjects with friends, and so there's so many things you can do in life, and beers is just one of them.
And photography, what type of photography?
Well, I am very big into exploring all kinds of photography. So going out and finding really, really beautiful places, and also finding, photographing even things which are really small, like a flower or something like that.
Macro even.
Yeah. So I'm really into all kinds of things. But I think it's
So
one
you're a
of
Sony guy, right?
Are you Sony guy?
Are you Sony guy?
No, I'm a Canon guy. I love the colors of the Canon. I love the colors.
He's a Canon guy.
I'm very into colors actually. So I'm very keen on getting. I had this problem with the computers and things like that, because a picture is starting as analog and then it becomes a representation in digitalized form as Ada Lovelace, goes into the computer. And then it has to come out also, in the same kind of,
In the display.
Yeah, and that is a complicated thing. So don't get me started on that subject. So you can speak, but at least I work for Nvidia, so I got access to excellent graphics technology. But still,
Still not happy.
I am actually running Canon cameras, so I'm not into.
But are you a full format guy?
Yes,
Yes.
I'm a full. Don't you see that? I'm XXL size, so big.
Full stack, full format.
Stack. I'm full stack, full format Superpod. That's who I am. I love it. That's a new T-shirt. Full format, full stack, Superpod. That's Leif's T-shirt. You're gonna have a T-shirt like that, Leif.
Sounds like a Muse song. So.
Yeah, that's good.
Okay.
Cool. And last question then. Anyone that you would recommend to come on this podcast, Leif, that you would be interested to listening to yourself?
Does it have to be a person in Stockholm or?
Preferably.
Yeah.
Preferably less, yes, because this is the format. We eat and drink together, so it needs to be on the table.
Someone who can get to Stockholm at least. I mean, like right now in Corona, it's a little bit tricky with the traveling. But Sweden maybe.
Now I think that in a year,
It will open up, and we will have it when we have the conferences. We will have it.
I hope so. We have data innovation in October, or we are planning to have it as a hybrid. So as soon as the conferences are open, then we will have like a lot of international speakers and etc. coming. So we will start inviting international people to.
So
come.
shoot.
Yeah. So let's start with a domestic first here.
And then go
we
for
can
the real guys.
Go for the real guys. It's up to you.
No, I think that one person that can be really interesting to invite to this podcast is a guy called Todd Dougherty. So it's one of those persons who are really into beers and really can talk about beers in hours and hours. But he also has spent his entire life working in companies who do work as visual effects, cinemas and producing movies and things like that. And he
CGI.
lives here in Stockholm, but he has worked all over the world in this kind of projects.
But he's a CGI guy.
Yeah, he's been in that industry for very long.
How do you spell his name?
The Todd, Todd.
Todd.
Yeah. And then it's like daughter, daughter, Eri, och sen Eri in the end. So
Daughtery.
yeah. Daughtery, yeah. So he lives here in Stockholm. He lives on Lidingö. So it was to be the fastest and simplest answer because he has a lot of stories to tell. And he can also talk much more about beer than I can talk about beer.
Nice.
Thanks.
Should bring Matthias and him together, I think.
And that is going to be a dangerous night, for sure.
It should be. Leif, the time is flying away, but it's been a true pleasure to have you here. I wish we could have spoken so much more about all the interesting stuff you're doing with Nvidia, about HPC and healthcare and all the things you're working with. But it's been a true pleasure. So thank you very much for coming here, and I hope you stay on and we can continue discussion.
We can continue with the after
work.
Yeah,
But,
let's do that. So yeah.
Now we get to the really interesting
Now we
discussion.
I have a couple of questions up my sleeve that we're gonna stay a couple of bit longer.
Good. Okay, thank you, and thank you to all the listeners who might have been listening into all of our chats. Then, so all about our views on where we have been and where we are going in this industry.
Thank you.
Thank you, everyone. Bye.